Welcome to Lecture 6 of Part 2 of the course Introduction to General Relativity. As you know, Part 2 is called Mathematical Preliminaries, and it is designed to equip you with the tools of differential geometry and Riemannian geometry, which are necessary for operating in warp spacetime, which is spacetime with gravitational fields turned on. This is also the 7th week, so Lecture 6 of the 7th week, or you can consider it the 43rd lecture overall. All right, the main reference for today's lecture, which is called Calculus and Manifolds Part 2, is Chapter 5, following pages from Nakahara's text. I'm using the 2nd edition. Carroll's notes on general relativity, Chapter 5, these pages, and Harding Analysis textbook, Chapter 2, following pages, can also serve as alternative references for today's lecture because they cover the equivalent amount of material. As usual, the lecture notes will be posted on the NPTEL-NOC website. And those who were looking for a little more depth and detail, including proofs of some of the results which I will discuss and I will omit, can consult Warner's excellent textbook on differential geometry, which is a graduate level math textbook. All right, for background, I will assume familiarity with the idea of smooth maps between manifolds. I'll assume familiarity with the notions of smooth vector, smooth covector, and smooth tensor fields. And I'll also, from time to time, quote results from multivariable calculus and theory of ODEs. Let's look at what's on the agenda for today. Our aim is to become familiar with the following concepts. First, we will learn about induced maps, namely the pushforward and pullback map. And I'll illustrate these in the setting of an immersion or embedding map, which is a smooth map. Then we'll learn about integral curves of a smooth vector field, the associated concept of a one-parameter group of diffeomorphisms, and finally, we will show that how integral curves of a smooth vector field can lead to the existence of a one-parameter group of diffeomorphisms, which are called flows. Once we get to flows, this will lead us naturally to the notion of a Lie derivative of smooth tensor fields with respect to a vector field. As you can see, L sub x of y means you're supposed to take the Lie derivative of the vector field y with respect to the vector field x. So we will define these quantities. And finally, we will look at the notion of a Lie bracket between, which is an operation involving two smooth vector fields, which is denoted by this bracket with the arguments x and y. Okay, and we will conclude our lecture here. All right, let's start with the notion of induced maps. We need to start with a smooth map between two manifolds. Again, what we have an m-dimensional manifold, big M, and a little n-dimensional manifold, big N. And F is a smooth map between the two. So under this map, a point P, which lies in M, gets mapped to its image, F of P, which is an N. And let me draw this for convenience. So you have M, which is a little m-dimensional manifold. You have N, which is a little n-dimensional manifold, and you have a point P, and which gets mapped to some point here. Let me call that F of P, the image. And then this point P is, of course, covered by some coordinate system, in which the coordinates of the point P is given by x, m real numbers, so x mu. All right. And similarly, the image point f of p is covered by some coordinate chart in N, under which the coordinates of this image point is y, which is a vector, which is a list of n real numbers, and they are indexed by alpha, y superscript alpha. All right. So when we have a smooth map, what happens is that the coordinates of this image point y or y alpha, they become smooth functions of this point, pre-image point x. Okay, so these are C infinity functions. That is what we mean by a smooth map. All right, so we have the setting, coordinates of the image point y are smooth functions of the coordinates of the pre-image point x. Okay, we have the setting, and the idea is that, well, this map induces, actually, the smooth map F induces a map between the vectors or tangent vectors at the point P and at the image point f of p. How do we see that? It's actually very easy. So consider a curve in M, which is x of t. So the t is the curve parameter. So as I vary t, I trace out the curve in M. Now under f, this curve gets mapped to another curve in N, which is given by y of t, where first I substitute y of x of t. So y of x is the smooth map f, but then x itself is a function of t on the curve. So we have y of x of t, or this is a function of t, ultimately a function of t. So we have y of t, which is given by this function. And then it's very easy to write down the tangent vector to this curve. So that will be given by dy alpha dt. These are the components of the tangent, if you remember last lecture. And then we can use chain rule because this is a composite function. Y doesn't directly depend on t, but y first depends on x, and then x depends on t. So we use chain rule to write down this relation. As you can see, this is the tangent vector at the curve in M, and this is the tangent vector of the image curve in N. So that I will call maybe alpha. Okay, so these components are given by these. And then they're connected by this Jacobian of the transformation. So this is how we relate the tangent to tangent vector at the curve in M. Under the smooth map F, it's related to some other tangent vector to the image at the image point, which is called t prime alpha, as I've written. Of course, this is for a tangent vector, but every vector at the point P is tangent to some curve. So we can generalize this formula or this rule to define something called the push-forward map, which is denoted by F with star downstairs, which is a map from the tangent space at P to the tangent space of the image point F of P. All right, so if V belongs to the tangent space at P, then F star of V will give you an element of the tangent space of the image point. And the formula is exactly the same, except for the tangent vector dy alpha dt, I've replaced it by V prime alpha. Okay, and dx mu dt, this component, I've replaced by V mu. So this is a general vector, not just tangent vector to this curve x of t, but in general vector. Okay, so general vector in t sub p of m is mapped to a general to a corresponding vector in the tangent space of the image point, and they are related. The components are related by this rule, in which you have to contract by the Jacobian. So one thing about the Jacobian is that this Jacobian matrix is not a square matrix, because remember the row index, so J superscript alpha, the row index, and subscript mu, which is the column index. This is not a square matrix because alpha can take values 1 to n, while mu takes values 1 to m, for which the inverse is not necessarily defined. And this notion of a push-forward map can be defined, can be extended not just from vectors to smooth tensor fields of rank p comma 0. Remember, tensor fields of rank p comma 0 can be thought of as a direct product of p copies of vector fields. P vector fields, if you take direct product, what you get is a smooth tensor field of rank p comma 0. So if for the vector, there is one factor of the Jacobian for product of p such vectors, naturally you would get the transformation rule would involve p copies of the Jacobian. All right, so t mu1 to mu p, this is an element of the gamma p comma 0 at m, smooth vector field in m at the point p, and then that is mapped to p comma 0 vector in n, which is given by t prime, and they're related by this rule with p factors of Jacobian coming here. So you have to contract them because the mu1s are mu's are contracted, alphas are free index. Okay, so this notion of a push forward, in which you take a vector in M and you push it forward to some vector in N, can be generalized to p comma 0, rank p comma 0 tensors, very simply. Now, okay, so the push. Let me draw this figure once again, just to as a preview. So the point P under F is map to some point f of p. And then the push forward map takes an element of the tangent space as p and maps to some element of, so if this is v, then its image and the push forward map is given by f with star downstairs, v. And then this pullback map would take a one form or a covector. So remember, a covector lives in the cotangent space, and you will take, let's say this is the covector, and the pullback map will take you from this one to an element of the cotangent vector here, cotangent space here. So for example, this one. So if this vector is omega prime, then it will lead you to this vector in the cotangent space, which I will denote by f with star upstairs. Okay, so push forward, the initial map was going from m to n. Push forward also goes from m to n, or t sub p of m to t sub fp of n, but the pullback goes in the reverse direction. Okay, so let me see how to construct this map. So this is the recap of the previous slide. Basically, we have a smooth map, we have the push forward map, and then the pullback map. How do we define? It goes in the reverse direction. So instead, from m to n, the pullback map goes in the reverse direction, n to m, and it's defined in this way. So the way you, so v and v prime is a push forward version, and then omega is some one form in n that is pulled back to some one form in w, w in m, and the way these are related is by this relation. Okay, omega of v should be equal to omega prime of v prime, and you can write this equation in coordinates. That is, omega of v would be nothing but omega mu v mu, and omega prime v prime is simply omega prime sub alpha with v prime superscript alpha, and then v prime alpha you can just plug in this right inside here. And then from equating both sides, you can see it is obvious that what you will get is this rule. This rule. Okay. So omega prime alpha is a cotangent, is a one-form field in n, and then you contract with the Jacobian factor, same Jacobian, del y alpha del x mu, same Jacobian. I'm not using the inverse, and you get back to the original manifold, in fact, cotangent space of the original manifold, and you get a one-form omega mu. Okay, so this is the construction of the pullback. It goes in the reverse direction of the push forward. Very simple, nothing complicated. And as I said before, just as in case of the push forward map, you can generalize to p comma 0 rank tensor. The pullback map you can also generalize to 0 comma q rank tensors. Okay, remember 0 comma q rank tensor fields are just you can think of them as a direct product of q number of one form fields. So q number of one form fields, which is the product. Then, as you can imagine, the transformation rule will involve q copies of the Jacobian. So here, as you can see, so this is t, little t with subscript alpha 1 to alpha n. This is an element of the smooth vector fields of rank 0 comma q in n, and then you pull it back to a 0 comma q rank smooth tensor field in m. So because this is indices mu1 to mu. Remember, mu indices are for m and alpha indices are for n. Okay, so the same Jacobian. Okay, forward Jacobian from x to y. The inverse Jacobian doesn't necessarily exist because this is not a square matrix. The Jacobian is not a square matrix. So the push forward and the pullback, you always use the forward Jacobian. Let me illustrate this idea of pushback and push forward with the immersion and embedding map. This we got familiar a little bit in the last lecture. So let me just define. So consider a smooth map F from M to N, again with same dimensionality, with a restriction, now with a restriction that N is greater than M. So N is a higher dimensional manifold compared to M, which is a lower dimensional manifold. Okay, this is the setting. You have a smooth map from a lower dimensional manifold to a higher dimensional manifold. And this map will be called an immersion if under the smooth map, the push forward map is 1 to 1. Okay, let me just draw this M, which is M dimensional, and then N, which is N dimensional, and then you have a map which takes you from any point on M to some point F of P. So F of P at N. Now, of course, the push forward takes you from the tangent space at P to the corresponding tangent space at F of P, right? If this map is 1 to 1, okay, in fact, it is 1 to 1, that is this tangent space M dimensional. Remember, the tangent space is M dimensional. Piece of P of M is the M dimensional vector space. Now, this vector space is isomorphically mapped to some M dimensional subspace of T of P of N. So remember, the tangent space here is actually N dimensional, and N is larger than N, so it's a larger vector space. What we are demanding for this to qualify as an immersion is that this mapping is 1 to 1 to M dimensional subspace of the tangent space at N. Okay, so let me give you an example to drive home this message. So this is our familiar example, S1, which is immersed in R2. So S1 is a circle, and we are going to immerse it into R2, which is the two-dimensional Euclidean plane, R2. And this can be done in many ways. One way is to choose. So remember, the circle is parameterized by theta. It's a one-dimensional manifold, so it only needs one coordinate to describe it. And R2 is, of course, given by two coordinates, x and y. X and y. So I've drawn these axes. And now one immersion map, one smooth map is x equal to cos theta and y equals sin theta. Of course, this is smooth because cosine and sine are smooth functions. They're same infinity functions of theta. So this is a smooth map. And of course, n here is 2 in this example, and m is 1. So n is greater than m. And so I can draw this. So if I do this immersion, it will be realized as some kind of a curve inside R2. Another way of doing it is, instead of doing this, you draw the figure of 8 curve, which is something like this. So here, x is given by a cos theta, same as before, and y, which is given by not b sin theta, but b sin theta cos theta. Okay. So if you map points on the circle to the plane via this second map, sometimes this figure of 8, which is sometimes known as the lemniscate of Gerono or lemniscate of Huygens, then you get this kind of an immersion. Okay. Why is this an immersion? As I said, each point, the tangent space, tangent vectors will be a unique correspondent. Let's check that. Theta equals pi by 2 and minus pi by 2, the tangent vectors. Let's say I'm going anti-clockwise. And the stop point, north pole, is theta equals pi by 2, and the south pole, when it comes around, is minus pi by 2. So here, it's very easy to see there is a one-to-one map. So the circle case is definitely immersion, but let's check the lemniscate. At theta equals 0, it starts from the origin, and then it goes around, and theta equals, so it goes around like this, goes bottom, and then comes back up, and goes back like this. So at theta equals minus pi by 2, the curve is going this way, so this is the tangent vector, and at theta equals plus pi by 2, sorry, this is theta equals plus pi by 2. And then when it's coming back, it is coming in. So theta equals minus pi. The tangent vector at the south pole is mapped here. and the tangent vector, the north pole, is mapped to this vector. So this is also a one-to-one map, and hence the lemniscate is also an immersion of the circle into R2. Okay. Now let's define an embedding. Immersion is fine, but there is a notion which is more useful, which is known as embedding. Now we will call an immersion to be embedding. That is, so it has to be an immersion to begin with. If in addition to f star being one-to-one, f is also one-to-one. Okay, so only one point of on M gets manifold to a point in N. You cannot have 2 points getting mapped to 1 point. That immediately disqualifies the lemniscate because both minus pi by 2 and plus pi by 2 are mapped to the origin here in the lemniscate. So this is a 2-to-1 map, and hence it is not an embedding. So the only embedding is this one. Okay, this is the embedding. This is an immersion, but not an embedding. Okay. If that is the case, then one can show the surface which is obtained as an image of M is actually a manifold. Hence, we call that a submanifold of M, M-dimensional manifold. So M-dimensional. And not only that, this M-dimensional image submanifold M of N, F of M, I'm sorry, is actually diffeomorphic to the original manifold M. Okay, we consider a smooth map from M to N. So the original manifold is now diffeomorphic to this image submanifold inside N. Okay, so this is IL-NOC proof. This involves the use of inverse function theorem, and one is the students should feel free to consult Warner's book to see the proofs. So this I wanted to just what we covered before. This is an embedding, but this is an immersion and not an embedding. Okay. So whenever we have an embedding, we get a submanifold. The original manifold is diffeomorphically mapped to a submanifold inside N. And in the next slide, we will learn that if such a thing happens, then if the big manifold, higher dimensional manifold has some metric, then that immediately implies a metric in the manifold M, which has been diffeomorphically mapped to some submanifold inside N. Okay, so we have a metric tensor on N. Now, in the last lecture, I mentioned the metric tensor is a rank 2 tensor field. So, rank 0, 2 tensor field. That means it will have as a basis the direct product of two coordinate differentials. So remember, coordinate differentials represent the basis element for one form, and if you take a direct product, that becomes a higher dimensional rank 0, p tensor, p 0, q tensor. So in this case, we have two rank 2, so we'll have the composition or direct product of two one form basis elements, and then this is the component g alpha beta of y. This is the number or a component. So we have a metric tensor on the higher dimensional manifold, and let's say we have some kind of a embedding in which some manifold M is mapped to some submanifold f of M inside. So f of M, which is, I'm sorry, I meant subset. So this, the image manifold, is actually a submanifold inside M, and the idea is I can give a metric on M using the notion of a pullback. That's very easy because this is a smooth map. That means we can define induced maps such as pushforward and pullback, and that is very simple. So let the embedding map is this is the smooth map. Y is a function of x. So x is a point on the M manifold. Y is a point, image point on N, and then this is the smooth map. Once this is given, it's very easy to write the Jacobian factors and contract them with g alpha beta, and you get the metric on M. So this is the metric on N, and using the pullback, we got a metric on M. Okay, N or f of M, whatever you call, because anyway they're diffeomorphic to each other. So if they're diffeomorphic to each other, then we consider them to be the same thing. And I'll give an example. I'll just follow up the same example which we discussed before. We had embedded S1 in R2 via this map. now instead of xy, I'm using y1 and y2 because y is a function of x. So y is I'm going to use as a space in which the mapping is done, the higher dimensional space, so R2. I'm using y and y2 as the coordinates, and this is the smooth map. And then we just apply the Jacobian rule to obtain the metric. But before that, let me discuss the metric R2. Most of you are familiar with writing the distance in R2 by this Euclidean or Pythagorean distance. So the 2 points in which their coordinates differ by dy1 and dy2. The distance squared is given by the sum of squares of dy1 and dy2. This defines the metric tensor in which the coefficients of dy1 square is supposed to give you g11, and the coefficients of dy2 square is supposed to give you g22. And the coefficient of the product dy1, dy2 gives you the metric component gy1, g12. But there is no such term, so we also have g12 equals g21 equals 0. All right. So this g is known for R2 very easily. As I said, g11 is 1, g22 is 1, g12 and g21 is 0. And then we just use this formula to write down the metric on S1 because y is unknown. So that will help us finding the Jacobian. And the g's also we have determined. So using these, we can perform this rule very easily. And then what we get is that the metric on S1 is just d theta theta, this component, times d theta square. So if I take a circle and if I consider 2 points which are separated in the angular coordinate by d theta, then this distance between these 2 points can be given by just d theta squared. Okay, on the circle, the distance between these 2 points, which is separated by the angular coordinate d theta, is given by the square of that. Okay, so this is how embedding and pullback metric works. This is what we use in GR a lot. Many times you will have subspaces inside some manifold, and you're supposed to find out what is the distance between point on the subspace. That it works by exactly using this pullback metric. The larger higher dimensional manifold has some metric, and then you're supposed to pull it back on the subsurface, on the surface inside it, to get the induced metric. Sometimes it is also known as induced metric. The pullback metric is also called the induced metric. Okay, and push forward and pullback maps are also called induced maps. All right, that concludes our discussion of induced maps, and we move on to the next topic, which is the notion of an integral curve or integral curves of a smooth vector field. So basically the idea is that we have a smooth vector field x, so that means the components of the vector x are function of the coordinates of the point at which the vector is located, and their smooth function meaning C infinity function. So the x mu's are smooth function of the little x's. So it's unfortunate that I'm using both big X for the vector field and little x. These big X functions, x mu's, they're n functions of n variables, and they're infinitely differentiable or continuously differentiable to arbitrary orders in each of these x's. Okay, that's what defines a smooth vector field. Now, the idea is that I consider a curve in the manifold such that the tangent vector to this curve at each point coincides with x. Any point you take on this curve, you find out the tangent vector, which is this, right? A curve is given x of t, little x, not big X. Okay, that means the coordinates of the point at t is the curve parameter. As I vary t, I get the coordinates of the point at which I'm on the curve, and this is the tangent vector that is always equal to the vector field big X. Okay, so this is the definition of an integral curve. Integral curve of a vector field is such that it's a curve such that the tangent vector at each point is equal to the vector field itself. Okay, right. So this is the defining equation. and I have to solve for this curve x of t. As you can see, this is a system of n first order differential equations in t, and it is an autonomous system of equations because the independent variable t does not appear here. Okay, at least not directly. Of course, little x's depend on t. This is what we are solving, but no, there's no explicit dependence on t. Okay, so this autonomous system of first order ordinary differential equation, ODE theory tells us this is solvable, and a unique solution is guaranteed to exist, provided we have this boundary condition, which is at some value of t, let's say t equal to 0, the x mu's are fixed. Okay, if this initial condition is given, then the solution is unique, and then a unique solution exists. Okay, and these are called integral curves. So this is the manifold, and each point you have some integral vector. Smooth vector field means that each point there is a vector, something like this. And the idea is through each point there will exist integral curves, which will such that the tangent vector will coincide with the vector field. Again, for here, for example, it would be something like this, and then for example here it would be something like that. So the integral curves will look like contour lines. They don't have to close. Here I'm drawing closed, but they look like contour lines. And of course, two integral curves can never intersect, because that means at the same point they have two different tangent vectors, which doesn't make sense. The tangent vector is unique. So two integral curves will never intersect. Okay. And let me demonstrate with an example. So let's consider the manifold to be the trivial manifold R2. Okay, we have R2, and we have some vector field in R2. So the vector field, its components are, because it's R2, mu will take value 1 and 2. So two components. First component is minus y. Remember, this is the basis vector, and the second component is x. Okay, so this is the smooth vector, and we are in R2. So then we are supposed to construct the integral curves of these, and that means you solve this equation. So the first equation will have minus y on the right hand side, corresponding to the vector field, and the second equation, dy dt, will have x. And this pair of equations can be easily solved. Most of you have done this either in high school or in college. This will give you the sinusoidal type of equations for both x and y. So the solution is something like this. X is a cos t minus b sin t. And y can be found out by taking derivative of x with respect to t, and with a minus sign, of course. I'm not writing them down. You can figure it out yourself. So this, then it becomes clear that the integral curves are circles. So let's say at some point on the x-axis, this value is x. Let's say x is plus 1. So the vector points to x component of the vector points in the minus y direction, but on the x-axis y is 0, so it doesn't have any component along the x direction. The entire component is along the y direction, something like this. Similarly, on the y-axis, its component will be along the minus x direction. And as you can see, here it will be something like this, here it will be something like that. And the smooth curve on for which these are all tangents to are going to be the circle. Okay, intuitively it is also clear. So I'll give some exercises so that you can get to practice computing or working out integral curves for a given vector field. All right, now let me discuss the notion of a one-parameter group of diffeomorphisms. So let me first state the definition. A one-parameter group of diffeomorphisms is defined to be a smooth map from R times M, so to M. So as an input, so we have phi, which takes as an input one real number and a point on the manifold. And then the output is also a point on the manifold. It also belongs here. Okay? Now this will, such a map, of course this in general this is not a one parameter group of diffeomorphisms. What qualifies such a map to be a one parameter group of diffeomorphisms if for a fixed t, if you fix t, so if you fix t, I'm going to denote that map. So t is not a variable anymore. Fix t, and then you have this. So this will map points on M to M. If this map points on M to M, if this map from M to M, so phi t is a map from M to M, if it is a diffeomorphism, that is, not only is a smooth map, but the inverse exists, and the inverse map is also smooth. If this is a diffeomorphism, and this map phi sub t for two different values of this real parameter, the composition is something like this. Phi t, phi s is same as phi sub t plus s. So clearly the order of t and s, order of composition doesn't matter because addition of two real numbers is commutative. So you can write phi of t composed phi of t of phi of s or phi of s of phi of t. What it means is that, remember the composition map phi t of phi s means inside you put phi s of t. But what is this? Remember what I just, this is nothing but phi in the original map t comma phi sub s of p, and this is nothing but phi t comma phi s comma p. Okay, so in terms of the function, this is what this composition means actually. This, okay, final result is u. Now this you have to show, or if it is, if the condition holds that this is same as phi t plus s starting from p or p. So this is the right hand side. So I'm writing in full gory detail. So the left hand side is this, and the right hand side is that. If these two turn out to be the same, only then does this map phi qualify to be called as a one parameter group of diffeomorphisms. Of course, it's, as I said, it's a commutative or abelian group. And an example I will give you, which most of you are familiar with, is the translation in R3. You can consider the translation symmetry, in which we can shift the origin. Let's say the point A, not this origin, any point can be shifted. So let's consider this map in which I take a point and I shift it by an amount t in the direction n. N hat is some fixed vector, and I take any point A and I move it to a point A plus t times the n hat. So displacing each point by in a fixed direction n by an amount t. So this you can easily check that both of them are true. As I said, the second condition means phi of t comma, instead of p you put phi of s comma p. Equals phi t plus s. Okay, this is the second condition. And you can check for the translation, this is indeed true. You can take this formula and see that it will obey this rule. Of course, this is a smooth map because you can infinitely differentiate with respect to t. So it's a diffeomorphism and invertible. You just have to put a minus sign. That's the inverse map. That is also smooth. So this is one example. Rotations in around the fixed axis can also be one parameter group of diffeomorphism. Now another related notion is that of an orbit. So the idea is we have this one parameter group of diffeomorphisms. Fine. Now let me fix a point P. And this point P is fixed, and let me vary T. Okay. If I vary t, I will trace out some curve, right? And this curve is called the orbit of p. Okay. Now, what we learned about is integral curves. Now, integral curves actually gives rise to an example or one instance of one parameter group of diffeomorphisms. These are called flows. Okay, that's very simple to see. The integral curve, I have so far denoted it t. But of course, initial point is needed. So some initial point is needed. Let's say the flow starts at t equal to 0 to x0. So instead of writing x, I'm using sigma because we're using x too often. So the integral curve, instead of x mu, I will use sigma mu of t. Okay, so this one can check satisfies both of these. Okay, both of these conditions. So the integral curves define the one parameter group of diffeomorphism of n, at least locally, and this is called the flow generated by x. You start from a point x0. Again, instead of the point I'm denoting by its coordinate, I'm using the coordinate as a proxy for the point. And then the integral curve of some vector x generates a flow. Okay, and this flow map, which takes as an input the initial point and the flow parameter t, gives you or is an example of one parameter group of diffeomorphisms. Both these conditions satisfied. You can check. Okay. Now, these flow maps are important because they lead to a notion of something called a lead derivative, which is very important in general relativity. So this is what we do in the next slide. So the setting is such that you have some initial point x0. And then you have two smooth vector field x and x. Let me redraw this. So at this point, I have a vector x and I have a vector y. Of course, these are vector fields, so they're defined at all points, not just at x naught. Now, the idea is that generate the flow from x naught using the vector field x, and generate another flow using y starting from the point x naught. Okay, so something like this. Okay, those flow the first flow I will call sigma, the other flow I will call tau. So here I have defined it. So the starting point is the same. T and S are the flow parameter, the parameter along these curves. Remember, these are just integral curves. So the curve parameter is S and T and S respectively. So these are the equations, right? X is the function of, instead of X, I'm using sigma because X we are using too often. And then you can ask the question, okay, if I take this vector y and I compare, because y is a vector field, it is defined everywhere. How does y change as I go along the flow of x? This is the question. How does y change as one proceeds along the flow? Now, from P to Q, let me go back to the diagram. So let me call this point Q, and let me call this point P. Okay, from P to Q, this is the value of y at Q, or this is the vector at Q. So you can ask, well, I mean, you can, in response, you can say that this is not a well-defined question. Why? Y at P lives in some vector space, the tangent space here, and y at Q lives in the tangent space there. And these two are two different separate vector spaces. There's no way I can compare vectors in two different vector spaces, right? So it's not a well-defined question. But if you hang on a little bit, I can make this question well-defined. It is true, the vector at P, y of P is not comparable to, directly comparable to the vector y at Q, but this flow is a smooth map from P to Q. So under this smooth map, I can use the push forward concept of the push forward to push forward this vector at y, vector at P to some vector f star. Okay, there exists a map between the tangent spaces. These two tangent spaces, they are different, but I can map them, map one to the other using the. In fact, I can push forward a vector from the tangent space at P to its cousin or its counterpart in the vector space or the tangent space at Q. And then now there is nothing stopping me to compare between y at Q and the pushed forward vector from P, also at Q. Okay, these two are the same space and I can compare them. So this basically gives you the idea of lead derivative. Okay, so use the push forward map under sigma, under the flow or the integral curve to push y of P to sigma of y, which will then lie at Q. And then sigma downstairs asterisk or star is the push forward. These two can be compared because they both lie at Q. This gives you the notion of a lead derivative of y with respect to s. So compare the value of y at Q, which is the so change in t when you go from P to Q. Change in t is epsilon. The flow parameter is changing by amount epsilon because we want to define a derivative. This is the point Q, which is infinitesimally up the flow from down the flow from P, not up the flow, down the flow from P. And then this is the value, this is the tangent vector, this is this vector field at the shifted point minus the pushed forward from the point upstream, which is this. And then you process this expression, which just requires a little bit of Taylor expansion. Please refer to the notes where I've done the detailed math. I'm not going to do it on the lecture itself because it's just high school algebra. Just Taylor expansion and then cancellations, which will lead you to the expression. So the lead derivative of the vector field y with respect to s measures how y is changing along the integral curve or flow generated by x. Okay. Now Lx of y. Okay. Now it turns out that this is also a vector because the difference between two vectors is a vector. So the lead derivative of a vector field is another vector field. Okay. So lead derivative of a vector field is another vector field. So it must have the vector index mu, and its components are given by can be computed from the components of x and y by this formula. Okay. This is the formula. So the lead derivative maps an element of gamma m, which is the family set of smooth vector fields, to another smooth vector field, L sub curly L sub x of y. Okay, so y gets mapped to curly L sub x of y. You can also do the reverse, in which you can measure how x changes along the flows of y. Okay, that will give you curly y of x. And as you can see from the formula, this will become minus of x of y, curly L sub x of y. Okay. So this is the simple notion, and you can ask the same question for a scalar field. Okay, I have a vector field which is generating a flow, and how does a scalar field change as they go along the flow? Now, the good thing about scalar field is it doesn't have a basis. It's not about vector space. It's not a vector space. It's just a number. I can always compare two numbers in two different places. Phi of q and phi of p. I can directly compare. So in that, I'm directly comparing. There is no push forward map involved here. And it turns out that if I process this expression, this is a definition of a lead derivative, how phi is changing as I go along the curve generated by x. Then the expression turns out to be this. Okay. So one thing to notice is that if when I take the lead derivative of a scalar field, I get a new scalar field. So curly L, the lead derivative operation, takes an element of a smooth scalar field and gives me back a smooth scalar field. By the way, smooth scalar field is a physics lingo for what mathematicians call a smooth function. Okay. In the previous lecture, I was talking about a smooth function. You can, I'm going to use smooth function and smooth scalar field, these phrases, terms interchangeably. They mean the same thing. Okay. Then you can extend the notion of a lead derivative to a covector or one form field. You can define lead derivative of a one form field with respect to a vector field. Again, the notion is same. The question is same. I have a flow generated by X, and I have a smooth covector field. Now my question is, sorry, big X. How is omega of X changing as I go along the flow generated by big X? This is the question. Again, you can set it up in the push forward, in the pullback way, because we can map various different. This is a smooth map for which the inverse is also smooth because it's a diffeomorphism. So I can define a pullback easily. Then you can come up with the expression, but I'm going to do it a bit indirectly by something we already know, indirect method. This is not a direct way. So notice that if I take a vector field y, then by definition of a one form field eats a vector field and gives you a function, right? Omega of y is the function. Omega of y is omega move y. Right? This is a real number. And because these are fields, this real number will also vary from location to location. That's why it's a function. That's why I meant it's a function. All right, so this is a scalar field. I know how to take lead derivative of a scalar field. I know how to take lead derivative of a vector field. This we did in the previous slide. Then, if I demand that the lead derivative obeys the Leibniz rule, then I can easily define the lead derivative or deduce. In fact, it's derived directly in a different way. They mentioned using the pullback map, but I can deduce indirectly what the lead derivative of the one form field is if I assume that lead derivative, just like the regular derivative, obeys the Leibniz rule for products, for differentiating products. That is, Lx of this omega of y is first Lx acting on omega acting on y plus omega acting on Lx of y. So this is like your Leibniz rule for differentiation, in which you have two quantities, product of two things, and the first term is when the derivative acts on the first quantity and leaves pairs the second one, and the second term is when the derivative skips the first term and hits the second guy. Okay, so Leibniz rule. If you use this and simplify both sides, you can easily obtain that the lead derivative of a one form field is given by this expression. Again, lead derivative of one form is another one form. So the lead derivative operation, unlike some of the other derivatives, which one you have encountered before, the exterior derivative, which changes the index by one extra. So a p form gets mapped to a p plus one form, and the covariant derivative, which is to come, which changes the rank of a vector field or tensor field on which it acts. The lead derivative does not alter the rank of the tensor field on which it acts. So we just saw the vector field, lead derivative of a vector field is a vector field, lead derivative of a scalar field is a scalar field, and now we see that the lead derivative of a one form field is another one form field whose components are given by this formula. Okay. Again, I'm not processing this equation to derive this. We can do that. It's easy. You just have to use these formula for the lead derivative of a scalar field and a vector field and look at the notes for the details. Okay, the details are there in the notes. We have had enough examples. We define lead derivative of vector field. We define lead derivative of scalar field, and we indirectly deduced the lead derivative of a one form field. Using the same trick, you can indirectly deduce the lead derivative of a general rank p comma q tensor. Again, you use the Leibniz rule, and this is the general formula, which is a bit complicated, but the pattern is easily recognizable. For every upper index, you should put a minus term, and for the form on every form index or lower index, you should put a plus term, something like this. Okay. The pattern is, if you look at stare at it for a few minutes, the pattern becomes obvious. Again, the derivation you can do yourself. I'll leave it as an exercise. If you're not able to do that, just look at the notes. The derivation should be given to you. All right, the final item in today's lecture is the notion of a Lie bracket, which will lead to the notion of a Lie algebra. This family of smooth vector fields in M can be turned into a Lie algebra if we introduce a composition rule, in fact, a Lie bracket, which is defined as follows. So, given two vector fields x and y, I can define a third vector field, which is given by the Lie bracket of two vector fields x and y, and they're given by x comma y within the square brackets. Now, a vector field, we know in the last lecture, the way I've introduced a vector field is that it's a linear differential operator. As such, every linear differential operator acts on some function f, right? If you recall the last lecture, this is how we define the vector field. So, and that definition I can rewrite once. So x, if it's a vector field, acts on a function f, because x is a linear differential operator. This action will be given by x mu contracted with the differential operator del mu acting on f. Right? This was the definition. Now, the Lie bracket is defined this way. The argument of x is now y of f. So this is, remember, x of f is another function. So that you have to feed it to x, and x is the differential operator which will act on that, minus the reverse order. First, you compute y of f, x of f, which is the function, and then feed it to y. And this difference you work out. And it turns out this is the same as Lx of y. Acting on f, I'm sorry. The Lie derivative of x and y. Okay? So we can forget about this for the time being, but this definition is enough. And then you can check that this Lie bracket satisfies all the three conditions necessary for this space of vector fields to be turned into a Lie algebra. Namely, this composition of this operation is satisfies bilinearity. It is linear in two arguments, very easy to see. If I replace y by y1 plus y2, this will split up, each term will split up into two terms, so bilinearity is obvious. Skew symmetry, if I reverse the roles of x and y, reverse the position of locations of x and y within the bracket, these two terms also get flipped, so it picks up a sign. And symmetry, and of course Jacobi identity, this I didn't write, but you can show that x comma y, if you have three vector fields, x comma y, most of you know what this is from your undergrad classes, plus cyclic permutations of x, y, and z. There will be two more terms in which x, y, z, then you take y, z, x, and the third term will be z, x, y. So x, this plus cyclic perms equal to 0. So very easy, you can just check this is true. Okay. So this bracket actually has a very special meaning, which is what will lead to a couple of important results in the next slide. So let's consider. So what this gives you physically or geometrically represents is the non-commutativity of the two flows. What do I mean by that non-commutativity? So here again we have the point x, and this is the flow generated by x, and this is the flow generated by y at this point x. Now consider the situation that you flow along from this point along the integral curve of x, or the flow generated by x, by an amount epsilon. And as soon as you get to this point, you flow along, you go along the flow of y at this point by an amount, flow parameter, delta. And then you do the reverse thing. First you flow along the integral curve of y by an amount delta, and you reach some prime, which I'm calling y prime, and flow along an integral curve of x by an amount epsilon. So non-commutativity means that if you go in two different ways, in which first you go along x and then you go along y, versus first you go along y and then you go along x, these 2 points are not going to be the same point. There's going to be a gap between them. Then these two flows are said to be non-commutative. then the flows will not be commutative. If the Lie bracket is 0 at this point, this separation will not be there. This dotted line, dotted segment on the graph is proportional to the Lie derivative. Again, the math steps, you can look at the notes. I have already written it there. This is just for illustration. I'm giving this diagram. The math is all there in the notes. You can look it up. Where indeed I've established that this red dotted line is proportional to this Lie bracket. Okay. Now this phenomena, keep this in mind. Keep this picture in mind when I go to the next slide. Now let's compute the Lie bracket for simple cases in which we have the coordinate basis x1 and the component is 1. So the basis vector is del x2 and the component is 1 as well. What is the Lie bracket of these two? So because the components are constant, x1 derivative x2 minus the reverse order, this is going to be 0 because the components are 1 which are constant. So the Lie bracket will turn out to be 0. Now remember, x1 and x2 are nothing but the tangents to the, you can think of them as the coordinate axis, okay, x1 axis and x2 axis, right? So this tells you that if we have in an n-dimensional manifold, if we have a set of n smooth vector fields, so in an n-dimensional manifold, if you have n number of smooth vector fields that are linearly independent everywhere, and the Lie derivative vanishes or the Lie bracket vanishes, then the integral curves can be thought of as a coordinate grid. So the integral curves of x will give you a coordinate grid. This is a result of physical importance. Given a manifold, how can we set up a coordinate grid? One is that if you are able to find n number of smooth vector fields which are linearly independent and the Lie bracket is 0, they commute with each other, then they will give you, their integral curves will give you a coordinate mesh or a coordinate grid. Okay? This is a theorem which is of importance. And then there's a related theorem which says that, now let's say we are in an n-dimensional manifold, but we have m number of vector fields, okay? M is less than n. So let's say we are not able to find n vector fields which are linearly independent and they commute. Let's say instead we find a subset m number of vector fields and they don't commute, but their Lie bracket is closed in the sense that among the, say, if I work out the Lie bracket of any pair of vectors in the set, it is equal to some linear combination of elements of the same set. So they are closed under the Lie bracket. So they form a subalgebra which is called a Lie subalgebra. Now, if this is true, then the integral curves of these m span a m-dimensional submanifold. Okay, the VI will span a m-dimensional submanifold of m. So they will give some kind of submanifold, subsurface, let's say, which is m-dimensional. And let's say this was n-dimensional. Okay, so this is an important result which this theorem we will use when we construct the Schwarzschild solution in GR. Okay, this important theorem that if you have a bunch of vector fields which are closed under the Lie bracket operation, then the integral curves of those vector fields will span out a submanifold inside the larger n-dimensional manifold. All right, so that will conclude our lecture. So this is a summary slide of what we did today. And next up is Mathematical Preliminaries Part 2, when we cover Riemannian geometry. That is differential geometry specialized to Riemannian manifolds. That is what the setting of GR is, actually. All right, let me stop here, and I'll see you next time. Thank you for your attention.